we are going to use what we have learned with exponential growth and decay to write models that represent real-world examples, real-world situations. So first, let's define our exponential growth and exponential decay once again, just to clarify what it is that we're talking about. Remember what exponential growth means. As x increases, y increases. So if you were to look at a graph, it's going to swoop up like that. And then for our exponential decay, as x increases, y decreases. So it's going to swoop down like that. So when I say as x increases, that means my x value is getting bigger and bigger and bigger. So as x increases, y increases. It also gets bigger and bigger and bigger. With exponential decay, as x increases, so my x values are getting bigger, my y values get smaller and smaller and smaller. Remember, I'm going to approach but not cross that x-axis. Now, we can write exponential models for growth and decay. Notice the formulas are basically the same. We'll talk about the formulas, but let's look at what each of the variables mean. So your a of t, that's the amount after t intervals. So usually we say per year. Both of the examples we're going to do today are per year. So it would be the amount after t years. A is your initial amount. That's what you start with. R is your rate of increase or decrease, always written as a decimal when you are putting it into the formula. And then T is your number of time intervals. So notice your difference between your two formulas is right there in the 1 plus or the 1 minus. For growth, you're going to add. For decay, you're going to subtract. And what that's coming from is 100% plus our rate of increase, but we're changing it over to a decimal. So it's, move your decimal 2 places to the left, it's 1, that's the 100%, plus your rate of change. And then here, we're subtracting because it is decay, it's going down, so we're subtracting. So that's the difference between our growth formula and our decay formula. It's just the plus versus the minus. Notice that the number of time intervals, again, years most of the time, is in the exponent, which is what makes this exponential. All right, let's look at two examples. So starting at example 1, Tyler starts a savings account with $500. The account earns 5% per year. Write an equation to model the amount of money in Tyler's account after t years and graph the function. So first of all, this is what's called compounded interest. We're earning 5% per year. So at the end of each year, that 5% gets added back in. So we are talking compounded interest, not simple interest, which is why we're using our decay model. So coming down here, our initial amount was 500. Our rate was 5%, which we're going to change to a decimal. And we want to know after t years. So t is our variable. So we're going to use our growth, because hopefully when we invest money, we're using growth. So I'm going to do capital A of t equals my initial times 1 plus my rate, because it's growth, to the t. And we can just shorten that to what? 500 times 1.05 to the t. Now make sure that t is an exponent. It's a superscript. It's small, and it's raised up into the exponent position. So this is our function that we're now going to graph. So the graph is actually pretty simple. Notice I'm only using my first quadrant because it doesn't make sense to have negative number of years, or, well, it would make sense to have a negative amount of money, but it doesn't in this case. So we're going to start with 500. That's our initial, so we're going to put right there at 500. And then what I'm actually going to do, notice my scale 0, 5, 10, 15. I'm going to go to my calculator and I'm going to plug in for 5 years because that's my next one. So I'm going to do 500 times 1.05. I'm going to come to the outside of that to the 5. I get 638.14. So I'm just guessing about where that's at. So 600 and then a little bit. And then I'm going to plug in for 10. So I'm just going to come back in. I'm going to delete out the 5. I'm going to put in 10, $814. So I'm going to go to 10 and go a little bit more than 18. And then just to make it as precise as possible, let's go ahead and do 15. 1,039. So I'm going to be just a little above the 1,000. And that's what it's going to look like. Now let's do our example with exponential decay. Again, it deals with money because money, for some reason, in our brains makes sense. So it's good to start these problems with money. There's plenty of other applications, and we'll look at some of those. Gina's car was $21,000 when new. So that's your A. That's your initial amount. It depreciates. That means it goes down in value. So this is a decay at a rate of 9% per year. So our time intervals are years. Write an equation to model the value of her car after t years and graph the function. So again, we're going to go to our model. A of t equals our initial amount. This time, because it is decay, we're going to subtract. And don't forget, we're changing that 9% to a decimal. Move your decimal 2 places to the left. Doing that subtraction, I'm going to get 21,000 times 1 minus 0.09 is 0.91. And again to the t. T is an exponent there. All right, when I graph it, my scale is way off, isn't it? We're going to have to change our scale. I didn't realize how off my scale was. So I'm going to go 21,000 is my initial. So let's change our scale here. I'm going to pause and change my scale. Okay, I fixed it. Really, all that needs to happen is I was off by a factor of 10. I had 2,500. I meant to have 25,000. So you really just need to add zeros in there, or you can just rewrite them. With my initial amount of 21,000, I know that I need to be somewhere around 21,000 on my scale. And I know I'm depreciating, so I need the values that are lower than that. All right, so fixing our scale, and then let's graph. So I'm going to start, my initial amount is 21,000. So let's put it about right there. And then I'm going to go to my calculator. My scale on the x-axis, the t-axis goes by 2. So 2, 4, 6, 8, 10. So I'm going to go to my calculator, and I am going to do times 2, or to the 2 rather, 17,390. So we're going to be somewhere between 15 and 20. So about right there. And then to the 4. So I'm just plugging in some points. 14,400. So just below the 15,000. Plugging in 6. Oops. 11,900, so about 12,000. Plugging in 8. 9,800, so just below 10,000. So it takes about 8 years to be less than half of the initial value. and then plugging in 10. And I'm going by twos because that's what my scale was. About 8,000. Let's go ahead and plug in 12, and then I think that'll give us enough. 6,700. So we're still above. And I'm going to go ahead and draw in from there. And there we go. So those are our exponential growth and decay models.